Assalamualaikum and hi everyone. Today we will continue chapter 4 forces 4.2 which is Newton's law of motion. Now let's look at the learning outcome 4.2 which is Newton's law of motion. By the end of this subtopic, students should be able to state Newton's law of motion and apply Newton's law of motion. Next, let us see the Newton's first law. The Newton's first law states that an object at rest will remain at rest or continues to move with uniform velocity in a straight line unless it is at open by an external forces or net force equal to total F equal to 0. Let us see the inertia. Inertia is the application of Newton's first law. What is inertia? Inertia is a tendency of an object to resist any change in its state of rest or motion. Inertia is a scalar quantity. You can see the example here. When the cardboard is pulled away quickly, the coin will drop straight into the glass. The inertia of the coin maintains its state of rest and drop into the glass due to gravity. Now, let us see the mass. Mass is a measure of body's inertia. Mass is a scalar quantity. The unit of mass is kilogram or kg. Mass is independent of location and mass is directly proportional to inertia. Now let us see the polygon of forces. There are three cases here. The first case is a particle in equilibrium as a result of two forces acting on it. Let's say the F1 is to the right and F2 is to the left. The F1 and F2 are equal in magnitude but opposite in direction. So when the particle in equilibrium, total F will equal to 0, which is F1 minus F2 equal to 0. Total F equal to 0 means that total Fx equal to 0 and total Fy equal to 0. Second case is a particle in equilibrium as a result of three forces acting on it. Let's say the F1 is to the right, F2 is downward, and F3 is leaning to the left. When the particle in equilibrium, so we can form the F1, F2, and F3 to form a closed triangle of forces with a condition. When we combine these three forces, it must connected with tail to head of the F1 and then tail to head of the F2 and then tail to head of the F3. And when the object is in equilibrium, so total F will equal to 0, where the F1 plus F2 plus F3 equal to 0. Same with the case 1. When total F equal to 0, it means that total Fx equal to 0 and total Fy also equal to 0. The third case is a particle in equilibrium as a result of four forces acting on it. So this is F1, F2, F3 and F4. Same with the case 2. If the particle is in equilibrium, it can form, all these four forces can form a closed triangle of forces. So total F equal to F1 plus F2 plus F3 plus F4 equal to 0. So total F means that total Fx equal to 0 and total Fy equal to 0. Here is the problem solving strategies for equilibrium of a particle. If a particle is in equilibrium, it means that total F equal to 0 or F net equal to 0. First, sketch a simple diagram. or force diagram, which means you sketch all the forces on the body. Next, sketch a separate free body diagram for each body if there are more than one body on the diagram. You need to follow the step to sketch a free body diagram on 4.1 that we already learned. Then, choose a convenient coordinate axis for each body and construct a table to resolve the forces into their components. Fourth step is to apply the condition for equilibrium of the particle in the component, which is total Fx equal to 0 and total Fy equal to 0. Finally, solve the component equation for the unknowns. Now let us see the Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, or A directly proportional to total force or inversely proportional to mass. The equation is A equal to total force over M, or total force equal to MA. Total force is a net force or effective force or resultant force. If the force acts on an object and the object is moving at a uniform acceleration, not at rest or not in the equilibrium, so F net equal to total F equal to MA. There are 5 steps of the application to the Newton's second law of motion. The first step is to identify the object whose motion is considered. Second step is to determine the forces exerted on the object. Third step is to draw a free body diagram for each object. Fourth step is choose a system of coordinates so that calculation may be simplified. And finally, apply the equation above for a long x-axis, which is total Fx equal to Max, or along y-axis, total Fy equal to May. The last Newton's law of motion is the Newton's third law. Newton's third law states that every action force has a reaction force that is equal in magnitude but opposite in direction. There are 4 cases here. The first case is vertical surface. So you can see the diagram here. And let's say A is the hand, B is the wall. So when the student push on the wall, it will push back with the same force. So we label it as FAB to the right and FBA to the left. The action force is FAB. FAB is a force by the hand on the wall. Okay, and then the reaction force is FBA. So FBA is a force by the wall on the hand. We can write down the equation is FAB equal to negative FBA. For case 2 is horizontal surface. Let's say an object lies at rest on a flat horizontal surface. So the action force is the weight. Weight of an object is exerted on the horizontal surface. And the reaction force is the normal force, where surface is exerted a normal force and on the object. When we want to write down the equation, so total F equal to N minus mg equal to 0, where N equal to mg. For the third case, which is inclined plane. Let's say an object lies at rest on a rough inclined plane. And as you already learned in 4.1, the x-axis is this direction and y-axis is to this direction. And when we sketch the direction of weight is always directed downward. Because the x is to this direction and the y is to this direction, so we need to resolve w to wx and wy. So from here, the action force is the y component of the object's weight, which is wy, is exerted on the inclined surface. So wy is the action force. For reaction force is the normal force. From the resolving vector, wx is equal to mg sin theta or w sin theta, and the equation of w is equal to mg. So wx equal to mg sin theta and wy equal to mg cos theta. So the equation will become total Fy equal to n minus Wy equal to 0 and n equal to mg cos theta. The fourth case is the motion of the leaf. The first case is the leaf moving upward at a uniform velocity. As you already learned in chapter 2, if the object moves with uniform velocity, the acceleration A equal to 0. Weight is the action force and will directed downward. And normal force is the reaction force and directed upward, which is normal force is perpendicular to the surface. Okay, from the first law of motion, so because this leaf moving with uniform velocity, so total Fy equal to 0 and Ay equal to 0. We label it as Ay and Fy because the leaf is on vertical motion. So n minus mg equal to 0. N equal to mg. Next case if when the leaf moving upwards at a constant acceleration. So you put the direction of the motion when the leaf is moving upward with constant acceleration. So total Fy equal to may. And the normal force is same direction with the acceleration. So normal force is positive. W is opposite direction to acceleration. So we put is negative mg. So it become n minus mg, so equal to ma. So the equation become n equal to m bracket a plus g. The third case of the motion of the leaf is the moving downward as the constant acceleration. So we put the direction of the motion which is directed downward. So total Fy equal to may. So because of the W is directed same direction with the acceleration, so the weight will use positive. And because of the normal force is opposite direction to the acceleration, so we put it negative n. So it become mg minus n equal to ma. So n equal to mg minus a. This is a few application of Newton's law of motion. I want to discuss about two cases here. The first case is an object moving in a rough horizontal surface. Let's say this object is being pulled to the right. So the direction of the motion or acceleration is to the right. Follow the external force. For the rough surface, there is frictional force acted to the object, which is opposite direction to the motion. Okay, so before we start to sketch the free body diagram, let us determine the forces acting in this object. So the weight is always directed downward and then perpendicular to the surface. So let's say this is a surface. Perpendicular to the surface is normal force directed upward. Okay, and just now is the frictional force, always opposite direction to motion, where the direction of the motion is to the right. So the frictional force is to the left. So we combine all these four forces to sketch a free body diagram. To sketch a free body diagram, you must start with a dot. Okay, so external force is to the right, frictional force is to the left, normal force is upward, and weight is downward. And don't forget to put the direction of the acceleration, which is to the right. Now we want to write down the equation of the x component and the equation of y component. Just now, the object is moving to x component or horizontal surface. So, which means this object is move to the x component. So, from the second Newton's law, total Fx equal to ma, which is total Fx equivalent to net force. Okay, you can use this rule if the force is same direction with the acceleration. You can use positive sign. Okay, if the force opposite direction with the acceleration, you can put it as negative sign. So from the free body diagram, the external force just now is same direction with A. So you can put positive F. But for the frictional force is opposite direction to the motion or opposite direction to A. So you can put it as negative F. To write down the equation, so external force, the positive F, minus F, frictional force, equal to ma. This is the equation of the x component. Okay, to write down the equation of y component, because the motion is on x component, so the y component equal to 0. So total Fy equal to 0. Okay, for y component, we have the normal force and weight. Normal force and weight. So the equation become n minus w, because normal force and weight are in opposite direction. So one you must put it positive, another one you must put it negative. So we use it as n minus w equal to 0. So n will equal to, because the w is equal to mg, so n equal to mg. Okay, the second case is for the rough inclined plane. So for the rough inclined plane, parallel to the inclined plane, this is the inclined plane. Okay, parallel to the inclined plane is the x-axis, and perpendicular to the inclined plane is the y-axis. Okay, let's say an external force is to this direction. So this is the direction of motion, which is same direction with the external force. So the frictional force is opposite direction to the motion. So the motion is to the following the direction of the external force just now. So frictional force is opposite direction to the motion. Okay, weight is always directed downward. Okay, and then the normal force is perpendicular to the surface. So the surface is here. So normal force is perpendicular to the surface. So this is the normal force. So because the x is parallel to the inclined plane, so we need to resolve the weight to the x component of weight and y component of x component of weight and y component of weight. Okay, so if you can see here, okay, let's say this is the theta. Let's say this is the 30 degree. Okay, so I made it a triangle here. Okay, so this is the weight. This is the top of the inclined plane. Okay, and then this is the y component of W. So 30 degree here, this is 90 degree, so 60 degree here. So the 60 degree here become 30 degree. Okay. So WY will use W cos 30 degree. And the WX will use W sin 30 degree. Okay, this is we will use this resolving vector when we want to write down the equation. Okay, so first of all, you need to sketch a free body diagram first. Okay, so this is the direction of F. The direction of normal force is perpendicular to the surface and weight is directed downward. Okay, the frictional force is opposite direction to the external force. And don't forget to put the direction of the acceleration. Okay, so to write down the equation of the x component, because this object is moving to the x component, so total Fx equal to ma. I already said just now, if the force is same direction with acceleration, we use it as positive sign. Opposite direction to the motion, we use it as negative sign. So the external force, we use positive sign. The frictional force, we use the negative sign. Okay, and when we want to write down the equation, we need to resolve the component of W to the WY. So just now I already resolved it, so become WY W cos 30 degree. How about WX? Okay, WX is W sin 30 degree. Okay, so which means on the X component, we still have another force. Okay, another force. Okay, which is WX. So the WX here is opposite direction to the motion, and we will use it as negative sign 2 for the WX. So the equation will become the external force positive F minus WX and minus frictional force equal to MA, where the WX just now is W sin theta and the W is equal to mg, so it become WX is equal to mg sin theta. Okay, so we rearrange this equation, so the external force will equal to MA plus mg sin theta plus with the frictional force. Okay, how about the y component? This object just move in the x component, so total Fy will equal to 0. So n minus Wy equal to 0, and I already resolved just now. The Wy is equal to mg cos theta. Finally, the normal force equal to mg cos theta. Thank you.